Hi, welcome to videos on rectifier and filter. The reference for this particular video is the fundamentals of microelectronics by Behed Razavi. So let us start with half-wave rectifier, which is usually referred as SWR. So the circuit diagram consists of a step-down transformer, a diode, and a load resistor. The input is the AC voltage, and the output will be measured at the junction of diode and the resistor. So this is the typical circuit that will be used for doing the experiment on half-wave rectifier, because in LTspice we don't have a transformer. So anyhow we want to have a sine source or AC source, so that we'll be realizing it using a V sine. So that is in LTspice. So here the difference between this circuit with transformer and the circuit with signal generator is, so only this is now replaced by a signal generator. So rest of the circuit remains the same. This is the working of a half-wave rectifier in ideal case. So during the positive half cycle, so we assume that diode to be ideal. So during the positive half cycle, diode switch closes. Diode is represented by a switch which is in closed position. So output is equal to input during the positive half cycle. During the negative half cycle, since diode is reverse bias, it will be open. The output voltage is equal to 0. So as it is seen in the output waveform, the dotted line corresponds to the input. So during the positive half cycle of the input voltage, so output follows the input, whereas the negative half cycle of the input voltage, the output is 0. So this is the time response of this half-wave rectifier in an ideal case, where we consider diode turns on for any voltages is more than 0. So this is the DC voltage. The DC voltage expected from a diode is V peak by pi, and this is the DC voltage, that is the average voltage of this waveform. And this is the transfer characteristics, where we are writing the input voltage on x-axis and output on the y-axis. You can see during the negative half cycle of the input voltage, the output is 0. During the positive half cycle, during the positive half cycle of the input voltage, output follows the input. That's why a slope of 1 is represented here. Let us see the working of a half-wave rectifier uh, in a typical case. So in a typical case, diode will not be an ideal diode. So we'll be considering a cut-in voltage of VD on, which will be usually 0.6 to 0.7 volts. So when the input voltage is more than VD on, this switch will be closed. So we are representing the diode by a model with a power supply VD on and this switch, which is open or closed depending on the input voltage. The switch is closed if the input voltage is more than VD on. The output voltage will be equal to Vp minus VD on, and this is the peak voltage what you are expecting. In general, you can write it as V in minus VD on. And during the negative half cycle, when the diode is off, that is switch is open, the output voltage is always 0. So that's what you can see here. So till the input voltage is VD on, the output voltage is 0 here. As the input voltage exceeds VD on, the switch closes, but you can see the input is certainly less than the the output voltage is less than the input voltage by a magnitude of VD on. That's what is here. So this is at the peak. So usually it is V in minus VD on. That's why you can see it is always less than the input by the VD on value. And you can see during negative half cycle it is still off. Again during positive half cycle, when the input voltage is more than VD on, it is turning on. So this is the transfer characteristics. So where the input voltage, if it is less than VD on, the output is still 0. When the input voltage is more than VD on, you can see the output is equal to V in minus VD on. So this is what is the VDC. VDC is given by the average voltage. The output is given by Vp minus VD on by pi. So the peak voltage is not Vp now. It's actually Vp minus VD on. So this is Vp minus VD on is the drop across the diode. So the average voltage will be Vp minus VD on by pi. This is the working of a typical half-wave rectifier by considering the cut-in voltage of the diode. Now we shall see the simulation of the same circuit using LTspice. To start the simulation of half-wave rectifier, so let us take a diode and place it as per our requirement. So I'm just placing one diode. So let me delete this diode. So I have deleted this. Let me select this diode, place it properly so that I can. So I need a resistor. So this resistor is connected. So I need a power supply. Power supply is there in this components, the last but one. So we have this power supply. Then you can wire it. So start from here, then click on this, start here, then make a turn. This you start here, stop, and then we are done with that. Now we need a ground point so that can be the reference for all the voltage measurements. So we can have this is done. Now I need to apply a sine wave. Go to this advanced. Let me select sine. So this doesn't have any DC. Let me give amplitude of 10 volt. Frequency, let us assume it as 50 hertz. You give it as, so we have made the settings for the sine wave. Maybe we can keep it here. And then before we start running, it will ask for the analysis setup. So this is, let us give it as 10 millisecond. So 10 milli itself is enough. It is 0. Give it as 1 microsecond. Say it is. So we need to edit the values of R. So that's why it is popping up an error. So let me give a resistance of 1 kilo ohms. Now I can start running. So this is the input signal, and you can see this is the output. If you can observe, the output is less than the input by VD on. So this is how a half-wave rectifier can be very easily simulated. You can also label the nodes here. So you can take a, of course you need to select this, take a node here, type it as input, place one here, and then place one more. And we can name this as output. Try to run it. Now you can see the input here. You can see this is V of in and this is V of out, so that you can easily differentiate which is input and which is output. So let us see what is the difference of input and output when it is at peak. It should be equal to VD on. Since we are interested in finding the difference particularly, so you can just zoom that particular portion, double click on the input. So both the plots are on, both the cursors are on input. Let me have one on input and one on output. Now you can see the difference. So at each and every point, since the x-axis both of them are same, so the difference between the input and output is 708 millivolts. So this is what is the VD on. So when the output voltage, when the diode is conducting, output is less than the input by the VD on. So let us go back to our presentation and continue with. So far we have seen the simulation, the working of half-wave rectifier and the simulation of half-wave rectifier. So let us now move on to the understanding the full-wave rectifier, which is usually called as FWR. It is a typical circuit diagram having a step-down transformer with a center tap, two diodes D1 and D2, and a resistor R. We can also rewrite this circuit by this way. You can see it is a similar circuit. Instead of writing a resistor over here, so it has been put over here, and you can see there is no connection existing between this point and this point. So the output resistor is actually going to the center tap. Now actually for simulating this Fourier rectifier, so we are using two sources as we don't have a center tap transformer in LTspice. We are using two transformers to realize the secondary of secondary center tap transformer. So this is V1, V2, and we have the similar circuit as in the previous slide. So we have a similar circuit, only this part of the circuit is replaced by two sources V1 and V2. Again, during the positive half cycle of the input voltage, that is V1, the V2 is actually negative half cycle. So when this is positive, so when V1 is greater than VD on, this switch is closed, that is this will be short circuited, whereas this is open. Since it is short circuited, the current flows from V1 through this diode D1 and goes to ground. So output is given by V1 minus VD on. So whatever the voltage you have, the output voltage is that voltage minus the VD on. So during the negative half cycle, it is exactly the reverse. During negative half cycle of the V1, actually V2 is positive half cycle, so D2 is turned on. So since the V1 is negative, this is open. The actually current flows through this D2, and then you can see it's again flowing through the resistor R in the same direction. Earlier also the current was going from V0 from this node down to ground. So now also it is going in the same direction. So we will have the output voltage coming in the same direction even during the positive half cycle of the input voltage and negative half cycle of the input voltage. The major thing to observe is during the negative half cycle of the input voltage also the diode D2 is on, so that will make the current to flow through this resistor in the same direction as when D1 was on. You can see when D1 was on, the current was moving in this direction, that is from top to bottom. Even when D2 is on, it is still flowing in the same direction. So that's why we have the current flowing in the output voltage in the same direction. So output is always on the positive half. These are transfer characteristics. Till VD on it is off. So both during positive half cycle as well as negative half cycle, and output is going parallel to the input voltage by a difference of VD on. So that's what you can see. So output is following the input, but less by VD on. So it's true both in positive half cycle as well as during negative half cycle. During negative half cycle, output is actually positive only. So let us see the simulation of same LTspice, that is Fourier rectifier simulation using LTspice. Let us see the simulation of Fourier rectifier. You can see we have connected a Fourier rectifier with two diodes D1 and D2, and this center tap transformer is realized using two sources of same magnitude, same frequency. You can see now it is 10 volt 50 hertz. Here also it is 10 volt 50 hertz. And we are doing a transient analysis. The stop time is 100 millisecond, and we have a maximum time step of 1 microsecond. So we would like to see the input voltage as well as the output voltage. So let us start simulating. Now let us try to see the input voltage which is available in this add trace. You can see there is an input, and you can add one more trace which is the output. You can see now this is the input and output voltage. Now you can see the input voltage is negative, the output is still positive. So you can just further zoom it up and then see. So how does the output voltage vary? Now you can see there's a difference of VD on between the output and input. So this is what is we observed in the circuit also. So this way we can able to very easily simulate Fourier rectifier. We can also observe the current flowing through the diodes D1 and D2. Now this is the current flowing through D1. You can see during the positive cycle of the input voltage, the current is flowing. During negative cycle, current through D1 is 0. Suppose if you see the other one, it's exactly the opposite. I can see this gray colored one shows the current is flowing during the negative half cycle of the input voltage, which is the gray one, whereas during positive half cycle that is 0. So both the diodes are conducting on alternate half cycles. So we'll see the bridge rectifier in the next video.